I'm going to spend a few minutes talking with you about what we're doing on computational behavioral phenotyping. I don't know why my presentation is running by itself, but that should be fine. Let's just start by basically parents explaining what's going on here, and then I'm going to give you some of the machine learning.
Grayson was our first child.
We thought maybe something was a little bit off pretty early.
We were told the wait lists for diagnosis with autism are really long, and I think they've only gotten worse from friends that I've talked to now.
The computer can see things that the human eye simply can't see. Well, when I first started doing autism research, the average waiting time for a parent who's worried that their baby or child might have autism is about a year. And so the challenge was, how do we come up with an app to be able to detect those early symptoms of autism, such as not making eye contact, not having normal facial expressions in a child's home? If a child is diagnosed at 18 to 24 months and provided 2 years of intervention, the average IQ gain is 17 points. So this has a huge impact on people's lives. And when I met Guillermo Sapiro, and he showed me that we could do what I've been doing in the clinic using a computer, that was an amazing moment for me.
So I've been doing computer vision and machine learning basically all my life. Using computer vision and machine learning, we wanted to see if we could help create an automatic analysis of autism and autism spectrum disorder.
Guillermo can use computer vision analysis to assess things like facial expression and attention. And so we built a set of movies that elicit these behaviors. And then we can show these on either a smartphone or a smart tablet and use the camera in the device to measure the child's response.
Data gets sent out from the phone to the cloud, and then we would be able to analyze that data, run it through our algorithms to produce our estimates of where the person is looking at. Now that we have this tool, what we hope to do is combine the eye tracking data, the gaze data, along with the motion, and jointly see if they can help in the assessment of the risk of autism.
Families simply don't have access to the professionals that they need. The idea that we could use technology to increase access, that's just a wonderful thought to me.
Every minute, every hour that you're able to implement those strategies, that's helping your child learn that social development and learn it with you. And as a parent, that is really rewarding.
Yeah. I think that if we can do just a small thing to change one kid, I think I would go to sleep with a smile. So thank you. Let me just explain a bit what's going on behind the scenes. We created a very large team at Duke University. You see some of them here. Jerry Dawson is our clinical partner. And we basically deploy in pediatric clinic. We have collected data over thousands of kids already, because we also deploy at home. Either you download and then you get access, or we are in pediatric clinics. So this is not a lab test. This is actually in the field, in the pediatric clinics, inside the hospitals at Duke. We have the kids play for about 10 minutes with different stimuli, including a game that they're playing with, and I'm going to show you in a second. And then we use the cameras to analyze. So the basic idea is that the kids come, sit in front of their the device. We use the front-facing cameras Jerry was describing. Then we we do computer vision and machine learning, and then we try to integrate and just try to do analysis. And let me just tell you some of the results that we've been getting, just a couple of things that we published in the last few months. The main take-home message is that it's working. This was a very large experiment that we try to do, but it's actually, we've been observing that it's actually working and it's very scalable because it's just a small device. So one of the things that we're doing is we're doing on-device basically gaze analysis, and then we can combine it. And as you can see here on the right, we basically have, for example, stimuli that have a social component, a person on the right, and have a toy on the left. Kids with autism normally tend to look at the left. Typically developing kids will look at the right. We have a symmetric picture, and we also have a conversation, and we look if they're alternating their gaze. And if we combine that and everything, so there is no expensive devices here, everything is just a phone or a tablet. If we combine the gaze analysis that we get from these 3 movies, each one is about a minute, we get about a 0.9 AUC. So just this very simple, once again, you just deploy a phone or a tablet as we're doing in the clinic, and then you just collect gaze using machine learning. And we only look if the kid is looking to the left or to the right. That's all what we care. We're not looking at the eyes or the mouth. We're just looking left or right. So very coarse level, we get about, as I say, a 0.9 AUC. So this is one example. Another example of what we're doing is actually, you see here screenshots of the different movies that we're doing, and we're tracking basically the face, and we're computing the facial dynamics. So we are seeing how predictable. So we're not talking about affect here. We're talking about using computer vision and machine learning to understand the complexity of your facial dynamics. And here you see some of the results. We just published these. So TD is typically developing kids, and ASD is autism spectrum disorder. These are 4 movies, social movies. So movies that have a social component, a person in them. And this is the distribution. And you see that the dynamics, the complexity of the facial movement that kids that have been diagnosed with autism do is much higher than the complexity of the facial movement of typically developing kids. And this is basically mostly manifested on the eyebrows. There is a lot of movement complexity, and in the mouth. Contrary to that, if you present a non-social movie, basically, as you see here, for example, just a dog or a puppet, you actually don't see such a difference on the dynamics, and we see here on the right. So basically, what we found out is that the complexity of facial movements, when the stimuli is social, basically kids that have been diagnosed with autism are basically having very complex facial movements. And as I say, the distributions are very different. For those that want to know a bit more of the technical details, so we use computer vision and machine learning to track the faces, and then we use what's called the multi-scale entropy to measure complexity, so standard tools from information theory. So we use gaze, we use facial dynamics, but as I mentioned, we also have a game. And the game is actually very simple. They have to pop bubbles, and there is an animal inside the bubble. So I can just play it again. It's kind of fun game. They laugh playing it. And you see when she's popping, there is actually a bubble, basically an animal coming out. And then we measure everything you can think about measuring. What is their accuracy, how frequently they pop. And here you see some of the results. The one I want to point out mostly is that we run these for kids that actually not only have autism, but actually have autism and ADHD. So basically have a comorbidity. And you see here basic kids that have autism and kids that have the comorbidity. And for example, the number of touches that the kids that also have ADHD is much larger. basically the error when they try to pop the bubble, they actually kids that have ADHD made a much larger error, and also they kind of apply more force to pop it out. So there is a lot of difference, and of course there is also differences between typically developing and ASDs. So we cannot, with this app, we not only basically look at their behavior, their facial behavior on gaze, but also we're starting to do fine motor and seeing differences. And in particular, when we actually look at a comorbidity, we can actually make those distinctions. And we just submitted this paper, but we have an early publication at the big autism conference. So these are just some of the things. As I say, this is about a 10 minutes video. I just show you 3 biomarkers: gaze, facial dynamics, and touch. But we have a few others. Some of them were published, some of them we're working on. The next goal is to combine all of them, because I basically show them each one separate. And also we have an effort that, as I say, these kids basically come into do pediatrics. So we actually have a lot of other information about them from the health records. And the idea is to combine that. And also just for you that because a lot of the audience is from Israel, we're now starting a collaboration with a group that works with Clalit. So the basic idea will be basically to deploy this hopefully very soon. One of the developers from the group is coming in March to my team, and hopefully to deploy this in Israel on a large environment and connect actually that with potentially with clinical records from Tipat Halav. So the basic idea will be just to go beyond this and use health records, potentially also health records from the parents, because as you know, there is a genetic component. I just want to finish by saying that this is work that is very hard work. Doing science with basically grown-ups is hard, but doing with kids is even harder. And we're so thankful to the families that participate in this. Even today, in the pandemic, families still volunteer to do this and just take their kids face covering down. They're only alone in a clinic with their kids. And we are actually deploying this in a number of different clinical studies, including in clinical studies that are showing basically interventions. And we actually also deploy already in South Africa on an intervention study. And as I say, we are planning on deploying in Israel hopefully soon. So thank you for your attention. I know I kind of ran through this, but I just wanted to give you a taste of what we're doing, and we'll be more than happy to answer questions or to talk with you offline.
Thank you very much. It was very interesting and inspiring, and I see the number of questions popping up. So I really have to choose between them, and maybe adding one of my side, from my side. I think the first one, well, let's first deal with those questions about how is it already commercially available? You were talking about the Israeli institutions that will make use of it, but maybe you can help this part of the audience that are interested in understanding where is it on the way to commercialize it.
For Duke University, this is still at the research level. We deploy in the pediatrics clinic, we deploy at home basically, but we are not yet incorporating this in the clinical practice of the doctor to make a decision system. That's actually the next step, but we are, a very serious medical team that has a very high threshold, and we're not happy to deploy until we don't have a complete validation study. So we have enough data, which for some people we say, okay, we're ready to fully deploy it into the clinical system. We believe that we need to collect more data. That's part also of the partnership in Israel, just to collect more data and just to be very safe. These are very sensitive topics. We're talking about children, and we believe that you have to be sure to the 10th power before you deploy anything that relates to children.
And you believe that it is going to get the FDA approval and replace this phase of the doctor detecting or
Great point.
diagnosing?
We are never towards replacing a doctor. Absolutely never. This is to improve information and to improve access. So you could think potentially, and I'm not saying that this is the direction to go, but you could think using this for what's called triage. So you do it at home, and depending on the score, you get to see a doctor in 5 minutes, or you get to see a doctor in a month, which is very important already. What Jerry mentioned in the movie, to actually, there is such a big waiting time that maybe we can do triage and just help that. Or, also parents say to the doctor, this is why I'm concerned, because this app has shown me, here it is, that my kid is basically having some motor challenges, and here are the results. So this is to augment the doctor, to help the hospital, is never to replace the doctors.
And do you think, well, I know it's very important to diagnose it as soon as possible, the very early stages, because the time to do some improvement it's the very early years, maybe 1 to 3 first years. Do you think such an application could be also in improving the performances of the child? Something with the feedback that you can measure, like you diagnose, but make it diagnostic like in real time, and then make him play or react to things that you stimulate him other way.
Great.
Part of the improvement.
Yeah, great question, both. We have 2 projects that are relevant. One is that currently, I forgot, I think, to mention, this is going from 18 to 30 months, 18 to 30, and that's because that's the age today that actually the diagnosis is done. We have a new project that we're actually moving this to 12 months. So we're trying to see how we can do it before. And then we have another project, and the group in South Africa, for example, is using the app for that, to say, okay, if these kids are already in treatment and the treatment is behavioral, do we see the changes in the app? And can we provide feedback? Because a lot of the autism treatment is behavioral, is coaching, and is done by the parents. Could we potentially use this down the road to say to parents, hey, we see their gaze is improving, you're doing an awesome job, but we see that the touch, they keep doing the same performance on the game, maybe we need to stress a bit more of that. So yes, we have kind of 2 projects very early on. We are very optimistic, but it will take a while to get us this data that we believe that we're ready to deploy in basically as part of the clinical practice.
Okay, thank you. It's all very inspiring. There were some questions about challenges under the field of computer vision, like all kinds of biases, different faces and different environments. How did you tackle that?
So yeah, great question. I know we're running out of time, but let me just tell you why there is a challenge. You tell an adult, look at the screen, and the adult will do this. You tell a child, look at the screen, and the child will do this. So this is something that computer vision has to deal. So we have to be able to filter data to understand reliability. So if you look at our code, I say 10 minutes. Normally, we might be using 7 minutes of that. So we have ways to detect what is reliable, what's not. This is actually one of the biggest challenges of computer vision, working with children. They do whatever they want, not what we researchers want. So we have a lot. We have kids that watch the entire movie like this. We need to deal with that. So yeah, it's a big challenge. I'm not saying we solve it, but we are in a good direction.
Great, great to hear, and thank you for your lecture and then your answers. It's a fascinating area. I think we're going to see a major progress with your research and some other research that I am familiar with. So I wish you great success with that, and we're expecting to see it
absolutely
and deployed in our healthcare environment.
Yeah, and let me just finish by saying that there, as you said, there are other groups, René Vidal at Johns Hopkins and others, and people at Emory, actually, Amy Klein, who is like me, half Israeli at Emory. I mean, there are other groups doing fantastic job in this area, and encourage those interested either to contact me or to look at their work. We're not alone here. And we should not be alone. This is an important problem. The more people work on this, the better.